In this lecture, we start our systematic study of Bayesian inference. We will first talk a little bit about the big picture, about inference in general, the huge range of possible applications, and the different types of problems that one may encounter. For example, we have hypothesis testing problems in which we are trying to choose between a finite and usually small number of alternative hypotheses. Or estimation problems, where we want to estimate as close as we can an unknown numerical quantity. We then move into the specifics of Bayesian inference. The central idea is that we always use the Bayes rule to find the posterior distribution of an unknown random variable based on observations of a related random variable. Depending on whether the random variables are discrete or continuous, we must of course use the appropriate version of the Bayes rule. If we want to summarize the posterior in a single number, that is, to come up with a numerical estimate of the unknown random variable, we then have some options. One is to report the value at which the posterior is largest. Another is to report the mean of the conditional distribution. These go under the acronyms MAP and LMS. We will see shortly what these acronyms stand for. Given any particular method for coming up with a point estimate, there are certain performance metrics that tell us how good the estimate is. For hypothesis testing problems, the appropriate metric is the probability of error, the probability of making a mistake. For problems of estimating a numerical quantity, an appropriate metric that we will be using a lot is the expected value of the squared error. As you will see, there will be no new mathematics in this lecture, just a few definitions, a few new terms, and an application of the Bayes rule. Nevertheless, it is important to be able to apply the Bayes rule systematically and with confidence. For this reason, we will be going over several examples.
Before we get going with our discussion of inference methods, it is worth looking at the big picture for some perspective. So far, we have concentrated on ways to analyze probability models, this part of the picture. If our model has been selected in a careful way, then it should also be relevant to the real world and help us make predictions or decisions. But how do we know that this is the case? This is why we need to look at data that are generated by the real world and then use these to come up with the model. This is what the field of inference and statistics is all about. This field has undergone a radical transformation in recent years. I will exaggerate a little, but in the past a statistician might be called to look at problems such as this one. You're given data on a few patients and you need to figure out whether a certain treatment is effective or not. But today, a statistician lives in a dreamland. There are tons of data that are generated everywhere. These allow us to build quite detailed, large models involving thousands of parameters. And we do have the computational power to do all that. In this landscape, the opportunities for a statistician are endless. So let me give you a small representative sample. In a somewhat traditional setting, one designs a data collection method and then uses these data to make a simple prediction. This is the case, for example, in polling, where the purpose is to predict the outcome of an election. Another field is marketing and advertising, where the situation is somewhat similar, except now we want to make predictions not for a population as a whole, but for each individual consumer. And a particular application has to do with so-called recommendation systems. You collect ratings that people give to movies, as in a famous competition that was announced by Netflix. So you have data for every movie and the people who have watched them. You make a note of what rating that person gave to a particular movie. And now, after you collect huge amounts of data of this kind, you try to use this information to guess whether, for example, this person is interested in this particular movie or not. This is a quite difficult problem, a quite complicated one, and it gave the community an opportunity to develop fancier and fancier combinations of methods in order to come up with good predictions of unknown entries in this table. Another field is, of course, finance. The markets are truly uncertain, and there are quite complete historical data, lots of them. How do we use these data to make predictions? Coming now to the natural sciences, a revolution has been taking place in the life sciences. There are tons of genomic data to be processed to find out what combination of genes causes what disease. Or we may want to find out the details of the chemical reactions inside the living cell. And there is an upcoming new frontier in neuroscience where there will be vast amounts of data that will be generated. These will consist of brain measurements, of measurements of what each neuron is doing, and hopefully these will lead us one day to finding out what the brain really does and how it works. In the sciences, the list is endless. It goes on and on. In modeling climate and the environment, scientists are using huge models these days, which they try to calibrate using lots of available data. And in physics as well, scientists use fancy inference methods trying to find needles in a haystack, like rare particles or remote planets. Finally, engineering is a fight against noise. Engineers try to make devices that will work in uncertain environments. The field of signal processing is a prime example where the generic question is to recover the content of a signal. For example, the content of a radio transmission when a signal is received after it gets corrupted by noise. I could go on and on for hours generating lists of this kind, but we have to stop somewhere. The bottom line is that the opportunities and the needs are vast. For this reason, we will look into the core methodologies that come into play. Fortunately for us, the fundamental concepts and approaches turn out to be the same independent of the particular application. Before we dive into the heart of the subject, I want to make a few comments on the different problem types that show up in the field of inference. You can think of a general distinction between model building versus making inferences about unobserved variables. We said a little earlier that one of the main uses of the field of inference is to construct models of certain situations. But in many cases, we already have a model. On the other hand, there may be variables that are unknown, that are unobserved, variables that are part of the model but whose values are not known. In such cases, we still want to use data to make some predictions or decisions about those unobserved variables. So model building might or might not be part of the problem that we're dealing with. To illustrate the difference between these two versions of the problem, let us think of a concrete setting. You have a transmitter who is sending a signal, call it S, and that signal goes through some medium. It could be just the atmosphere. And what that medium does is that it attenuates the signal by a certain factor A. And then as the signal travels, it also gets hit by some noise, call it W, and what the receiver sees is an observation X. So this situation is described by this simple equation here. This situation often brings up the following inference problem. We want to find out what the medium is. How do we do this? We send a pilot signal S, that is a signal that we know what it is. We observe X, and then using this equation and knowing that W is random noise coming from some distribution, we try to make an inference about the variable A. So this is an instance of model building. We are trying to make a model of the medium that's involved. But we can also think of a different problem. Suppose that we know what the medium is. Perhaps we already went through this particular phase here, but we're sitting at the receiver and we do not know what has been sent, and we want to find out what S is. So we are looking again at this equation. This time we know A and we're trying to make inferences about S. You notice that these two versions of the problem are essentially of the same mathematical structure. We have a linear equation. In one case, we know S, we want to find out A. In the other case, we know A, we want to find out what S is. So even though the interpretation of these two problems are quite different, the mathematical structure is exactly the same. This is fortunate. It means that one and the same methodology will be applicable to both types of problems. There is another distinction between problem types which turns out to be a little more substantial. There are problems that we call hypothesis testing problems. In those problems, the unknown takes one out of a few possible values. That is, we may have a few different alternative models of the world, and we're trying to figure out which one of those models is the correct one. We're going to decide in favor of one of the candidate models, and what we want to achieve is that we make a correct decision, or if not, we want to have a small probability of making an incorrect decision. An example of this kind is the radar detection problem that we had discussed in the very beginning of this course, in which we were getting a signal, we were getting a radar reading, and the question was to make an inference whether the radar is seeing an airplane or whether an airplane is not present. So in hypothesis testing problems, we're essentially making a choice out of a small number of discrete possible choices. Instead, in estimation problems, the unknown quantities are more of a numerical type. They could even take continuous values. And what we want to do is to come up with an estimate of an unknown quantity that is close to the true but unknown value of the quantity that we're trying to estimate. So here our performance objective is in terms of some kind of distance function. We want to be close to the truth, and typically we have a continuum of possible choices. That is, our estimates can be general real numbers. Generally speaking, these two types of problems, hypothesis testing and estimation, have some significant differences in the way that they are treated, as we will be seeing next. We can finally go ahead and introduce the basic elements of the Bayesian inference framework. There is an unknown quantity which we treat as a random variable, and this is what's special and why we call this the Bayesian inference framework. This is in contrast to other frameworks in which the unknown quantity theta is just treated as an unknown constant. But here we treat it as a random variable, and as such it has a distribution. This is the prior distribution. This is what we believe about theta before we obtain any data. And then we obtain some data which are some observation. That observation is a random variable, but when the process gets realized, we observe an actual value, numerical value of this random variable. The observation process is modeled, again in terms of a probabilistic model. We specify the distribution of x, but we actually specify the conditional distribution of x. We say how x will behave if theta happens to take on a specific value. These two pieces, the prior and the model of the observations, are the two components of the model that we will be working with. Once we have obtained a specific value for the observations, then we can use the Bayes rule to calculate the conditional distribution of theta, either a conditional PMF if theta is discrete, or a conditional PDF if theta is continuous. And this will be a complete solution, in some sense, of the Bayesian inference problem. There is one philosophical issue about this framework, which is where does this prior distribution come from? How do we choose it? Sometimes we can choose it using a symmetry argument. If there's a number of possible choices for theta and there's reason to believe that they're all equally likely, we have no reason to believe that one is more likely than the other, then the symmetry consideration gives us a uniform prior. We definitely take into account any information we have about the range of the parameter theta. So we use that range and we assign 0 prior probability for values of theta outside the range. Sometimes we have some knowledge about theta from previous studies of a certain problem that tell us a little bit about what theta might be, and then when we obtain new observations we refine those results that were obtained from previous studies by applying the Bayes rule. And in some cases, finally, the choice could be arbitrary or subjective, just reflecting our beliefs about theta, some plausible judgment about the relative likelihoods of different choices of theta. Now, as we just discussed, the complete solution or a complete answer to a Bayesian inference problem is just a specification of the posterior distribution of theta given the particular observation that we have obtained. Pictorially, if theta is discrete, a complete answer might be in the form of such a diagram that tells us that certain values of theta are possible with certain probabilities. Or if theta is continuous, a complete solution might be in the form of a conditional PDF that again tells us the conditional distribution of theta. To appreciate the idea here, consider the problem of guessing the number of electoral votes that a candidate gets in the presidential election. The electoral votes are certain votes that a candidate gets from each one of the states in the United States, and there's a certain number that a candidate needs to get in order to be elected president. One possible prediction could be a statement that I predict that candidate A will win. But actually a more complete presentation of the results of a poll could be a diagram of this kind, which is essentially a PMF. Here, a particular pollster collected all the data and gave the posterior probability distribution for the different possible numbers of electoral votes. And this diagram is a lot more informative than a simple statement that we expect a certain candidate to get more than the required electoral votes. So what is next? As we just discussed, the complete solution is in terms of a posterior distribution, but sometimes you may want to summarize this posterior distribution in a single number or a single estimate. And this could be a further stage of processing of the results. So let us talk about this. Once you have in your hands the posterior distribution of theta, either in a discrete or in a continuous setting, and if you are asked to provide a single guess about what theta is, how might you proceed? In the discrete case, you could argue as follows. These values of theta all have some chance of occurring. This value of theta is the one which is the most likely, so I'm going to report this value as my best guess of what theta is. And using a similar philosophy, you could look at the continuous case and find the value of theta at which the PDF is largest and report that particular value. This particular way of estimating theta is called the maximum a posteriori probability rule. We already have in our hands a specific value of x, and therefore we have determined a conditional distribution for theta. What we then do is to find a value of theta that maximizes over all possible thetas the conditional PMF of this random variable capital theta. And similarly in the continuous case, it's the value of theta that maximizes the conditional PDF of the random variable theta. This is one way of coming up with an estimate. One can think of other ways. For example, I might want to report instead the mean of the conditional distribution, which in this diagram might be somewhere here, and in this picture it might be somewhere here. This way of estimating theta is the conditional expectation estimator. It just reports the value of the conditional expectation, the mean of this conditional distribution. It is called the least mean squares estimator because it has a certain useful and important property. It's the estimator that gives you the smallest mean squared error. We will discuss this particular issue in much more depth a little later. Now let me make two comments about terminology. What we have produced here is an estimate. I gave you the conditional PDF or conditional PMF and you tell me a number. This number, the estimate, is obtained by starting with the data, doing some processing to the data, and eventually coming up with a numerical value. Now G is the way that we process the data. It's a certain rule. Now, if we know the value of the data, we know what the estimate is going to be. But if I do not tell you the value of the data and you look at the situation more abstractly, then the only thing you can tell me is that I will be seeing a random variable capital X, I will do some processing to it, and then I will obtain a certain quantity. Because capital X is random, the quantity that I will obtain will also be random. It's a random variable. This random variable, capital theta hat, we call it an estimator. Sometimes we might also use the term estimator to the function g, which is the way that we process the data. In any case, it's important to keep this distinction in mind. The estimator is the rule that we use to process the data, and it is equivalent to a certain random variable. An estimate is the specific numerical value that we get when the data take a specific numerical value. So, if little x is the numerical value of capital X, in that case, little theta hat is the numerical value of the estimator capital theta hat. So at this point we have a complete conceptual framework. We know, abstractly speaking, what it takes to calculate conditional distributions, and we have two specific estimators at hand. All that's left for us to do now is to consider various examples in which we can discuss what it takes to go through these various steps. Let us now discuss in some more detail what it takes to carry out Bayesian inference when both random variables are discrete. The unknown parameter theta is a random variable that takes values in a discrete set, and we can think of these values as alternative hypotheses. In this case, we know how to do inference. We have in our hands the Bayes rule, and we have seen plenty of examples. So instead of going through one more example in detail, let us assume that we have a model, that we have observed the value of x, and that we have already determined the conditional PMF of the random variable theta. As a concrete example, suppose that theta can take values 1, 2, or 3. We have obtained our observation and the conditional PMF takes this form. We could stop at this point, or we could continue by asking for a specific estimate of theta, our best guess as what theta is. One way of coming up with an estimate is to use the maximum a posteriori probability rule, which looks for that value of theta that has the largest posterior or conditional probability. In this example, it is this value, so our estimate is going to be equal to 2. An alternative way of coming up with an estimate could be the LMS rule, which calculates an estimate equal to the conditional expectation of the unknown parameter given the observation that we have made. This is just the mean of this conditional distribution. In this example, it would fall somewhere around here, and the numerical value, as you can check, is equal to 2.2. Next, we may be interested in how good a certain estimate is. And for the case where we interpret the values of theta as hypotheses, a relevant criterion is the probability of error. In this case, because we already have some data available in our hands and we're called to make an estimate, what we care about is the conditional probability, given the information that we have, that we're making an error. Making an error means the following. We have the observation, the value of the estimate has been determined, it is now a number, and that's why we write it with a lowercase theta hat, but the parameter is still unknown. We don't know what it is described by this distribution, and there's a probability that it's going to be different from our estimate. What is this probability? It depends on how we construct the estimates. If in this example we use the map rule and we make an estimate of 2, there is probability 0.6 that the true value of theta is also equal to 2, and we are fine, but there is a remaining probability of 0.4 that the true value of theta is different than our estimate, so there's probability 0.4 of having made a mistake. If instead of an estimate equal to 2 we had chosen an estimate equal to 3, then the true parameter would be equal to our estimate with probability 0.3, but we would have made an error with probability 0.7, which would be a bigger probability of error. More generally, the probability of error of a particular estimate is the sum of the probabilities of the other values of theta. And if we want to keep the probability of error small, we want to keep the sum of the probabilities of the other values small, which means we want to pick an estimate for which its own probability is large. And so by that argument, we see that the way to achieve the smallest possible probability of error is to employ the map rule. And this is a very important property of the map rule. Now this is the conditional probability of error, given that we already have data in our hands. But more generally, we may want to compare estimators or talk about their performance in terms of their overall probability of error. We're designing a decision-making system that's going to process data and making decisions. In order to say how good our system is, we want to say that overall, whenever you use the system, there's going to be some random parameter, there's going to be some value of the estimate, and we want to know what's the probability that these two will be different. We can calculate this overall probability of error by using the total probability theorem and the conditional probabilities of error as follows. We condition on the value of x. For any possible value of x, we have a conditional probability of error, and then we take a weighted average of these conditional probabilities of error. There is also an alternative way of using the total probability theorem, which would be to first condition on theta and calculate the conditional probability of error for a given choice of this unknown parameter. And both of these formulas can be used. Which one of the two is more convenient really depends on the specifics of the problem. Finally, I would like to make an important observation. We argued that for any particular choice of an observation, the map rule achieves the smallest possible probability of error. So, under the map rule, this term is as small as possible for any given value of the random variable capital X. Since each term of this sum is as small as possible under the map rule, it means that the overall sum will also be as small as possible. And this means that the overall probability of error is also smallest under the map rule. In this sense, the map rule is the optimal way of coming up with estimates in the hypothesis testing context, where we want to minimize the probability of error. In the next variation that we consider, the random variable theta is still discrete, so it might, for example, represent a number of alternative hypotheses, but now the observation is continuous. Of course, we do have a variation of the Bayes rule that's applicable to this situation. The only difference from the previous version of the Bayes rule is that now the PMF of X, the unconditional and the conditional one, is replaced by a PDF. Otherwise, everything remains the same. A standard example is the following. Here we are sending a signal that takes one of, let's say, 3 alternative values, and what we observe is the signal that was sent plus some noise. And the typical assumption here might be that the noise has 0 mean and a certain variance and is independent from the signal that was sent. This is an example that we more or less studied some time ago. Actually, at that time we looked at an example where theta could only take one out of 2 values, but the calculations and the methodology remains essentially the same as for the case of 3 values. So in principle, we do know at this point how to apply the Bayes rule in this situation to come up with a conditional PMF of theta. And the key to that calculation was that the term that we need, the conditional PDF of X, can be obtained from this equation as follows. If I tell you the value of theta, then X is essentially the same as W plus a certain constant. Adding a constant just shifts the PDF of W by an amount equal to that constant, and therefore the conditional PDF of X is the shifted PDF of the random variable W. Using this particular fact, we can then apply the Bayes rule, carry out the calculations, and suppose that in the end we came up with these results. That is, we obtain the specific observation X, and based on that observation we calculate the conditional probabilities of the different choices of theta. At this point we may use the map rule and come up with an estimate, which is the value of theta, which is the more likely one. And then we can continue exactly as in the case of discrete measurements, of discrete observations, and talk about conditional probabilities of error and so on. Now, the fact that X is continuous really makes no difference once we arrive at this picture. With the map rule, we still choose the most likely value of theta, and this is our estimate, and we can calculate the probability of error, which for the map rule would be 0.4. Exactly the same argument as for the case of discrete observations applies and shows that this conditional probability of error is smallest under the map rule. And then we can continue similarly and talk about the overall probability of error, which can be calculated using the total probability theorem in 2 ways. One way is to take the conditional probability of error for any given value of X and then average those conditional probabilities of error over all the possible choices of X. Because X is now continuous, here we're going to have an integral. Alternatively, you can condition on the possible values of theta, calculate conditional probabilities of error for any particular choice of theta, and then take a weighted average of them. In practice, this calculation sometimes turns out to be the simpler one. Finally, we can replicate the argument that we had in the discrete case, since the map rule makes this term here as small as possible. It is less than or equal to the probability of error that you would get under any other estimate or estimator, then it follows that the integral will also be as small as possible, and therefore the conclusion is that the overall probability of error is again the smallest possible when we use the map rule. And so the map rule remains the optimal way of choosing between alternative hypotheses, whether X is discrete or continuous. In the next variation we consider, all random variables are continuous. For this case, we do have a Bayes rule once more, and we have worked quite a few examples, so there's no point, again, in going through a detailed examples. Let us just discuss some of the issues. One question is, when do these models arise? One particular class of models that is very useful and very commonly used are so-called linear normal models. In these models, we basically combine various random variables in a linear function, and all the random variables of interest turn out to be normal. For instance, we might have a signal, a noisy signal, call it theta, which is now a continuous valued signal. We receive that signal but corrupted by some noise which is independent from what was sent. And we wish to recover, on the basis of the observation x, we wish to recover the value of theta. And then there are versions of this problem that involve theta vectors instead of single values, so that theta consists of multiple components and where we obtain many measurements x. We will actually see in the next lecture sequence a quite detailed discussion of models of this type. And this will be one of our main examples within our study of inference. There will be another example that we will see a few times, and this involves estimating the parameter of a uniform distribution. So x is a random variable that's uniform over a certain range, but the range itself is random and unknown. And on the basis of observations x, we would like to make an estimation of what the true value of theta is. This is an example that you will see in our collection of solved problems for this class. So what are the questions in this setting? We wish to come up with ways of estimating theta. We form an estimator, and the main candidates for estimators at this point are, once more, the maximum a posteriori probability estimator, which looks at this conditional density and picks a value of theta that makes this conditional density as large as possible. And an alternative one is the least mean squares estimator, which just computes the expected value of theta given x. For any given estimator, we then want to characterize its performance. In this case, a natural notion of performance is the distance between our estimate or estimator from the true value of theta. And commonly, we use the square distance and then take the average of that square distance. So in a conditional universe where we have already observed some data, we might be interested in this particular expectation, which is the mean squared error of this particular estimator, given that we obtained some particular data. Or we can average over all possible data points that we might obtain, so that we look at the unconditional mean squared error, which is a measure of the overall performance of our estimator. We will be talking about these criteria and the mean squared error in a fair amount of detail in a subsequent lecture sequence. We will now go through an example that involves a continuous unknown parameter, the unknown bias of a coin, and discrete observations, namely the number of heads that are observed in a sequence of coin flips. This is an example that we will study in some detail now, and we will also revisit later on. And in the process, we will also have the opportunity to introduce a new class of probability distributions. This example is an extension of an example that we have already seen when we first introduced the relevant version of the Bayes rule. We have a coin. It has a certain bias between 0 and 1, but the bias is unknown. And consistent with the Bayesian philosophy, we treat this unknown bias as a random variable and we assign a prior probability distribution to it. We flip this coin n times independently, where n is some positive integer, and we record the number of heads that are obtained. On the basis of the value of this random variable, we would like to make inferences about theta. Now, to make some more concrete progress, let us make a specific assumption. Let us assume that the prior on theta is uniform on the unit interval, in some sense reflecting complete ignorance about the true value of theta. We observe the value of this random variable, some little k. We fix that value, And we're interested in the functional dependence on theta of this particular quantity when k is given to us. How do we do this? We use the appropriate form of the Bayes rule, which in this setting is as follows. It is the usual form, but we have f's indicating densities whenever we're talking about a distribution of theta, because theta is continuous. And whenever we talk about a distribution of k, which is discrete, we use the symbol p because we're dealing with probability mass functions. As always, the denominator term is such that the integral of the whole expression over theta is equal to 1. This is the necessary normalization property. And because of this, this denominator term has to be equal to the integral of the numerator over all theta, which is what we have here. So now let us move and let us apply this formula. We first have the prior, which is equal to 1. Then we have the probability that k is equal to little k. This is the probability of obtaining exactly k heads if I tell you the bias of the coin. But if I tell you the bias of the coin, we're dealing with the usual model of independent coin flips, and the probability of k heads is given by the binomial probabilities, which takes this form. And finally, we have the denominator term, which we do not need to evaluate at this point. Now, I said earlier that we're interested in the dependence on theta, which comes through these terms. On the other hand, the remaining terms do not involve any thetas, and so they can be lumped together in just a constant. And so we can write the answer that we have found in this more suggestive form. We have some normalizing constant, and here we keep separately the dependence on theta. Of course, this answer that we derived is valid for little theta belonging to the unit interval. Outside the unit interval, either the prior density or the posterior density of theta would be equal to 0. This particular form of the posterior distribution for theta is a certain type of a density, and it shows up in various contexts. And for this reason, it has a name. It is called a beta distribution with certain parameters, and the parameters reflect the exponents that we have up here in the two terms. Note that these parameters are the exponents augmented by 1. This is for historical reasons that do not concern us here. It is just a convention. The important thing is to be able to recognize what it takes for a distribution to be a beta distribution. That is, the dependence on theta is of the form theta to some power times 1 minus theta to some other power. Any distribution of this form is called a beta distribution. So now let's continue this example by considering a different prior. Suppose that the prior is itself a beta distribution of this form, where alpha and beta are some non-negative numbers. What is the posterior in this case? We just go through the same calculation as before, but instead of using 1 in the place of the prior, we now use the prior that's given to us. The probability of k heads in the n tosses, when we know the bias, is exactly as before. It is given by the binomial probabilities. And finally, we need to divide by the denominator term, which is the normalizing constant. What do we observe here? The dependence on theta comes through these terms. The remaining terms do not involve theta, and they can all be absorbed in a constant. Let's call that constant d, and collect the remaining terms. We have theta to the power alpha plus k, and then 1 minus theta to the power of beta plus n minus k. And once more, this is the form of the posterior for thetas belonging to this range. The posterior is 0 outside this range. So what do we see? We started with the prior that came from the beta family of this form, and we came up with a posterior that is still a function of theta of this form, but with different values of the parameters alpha and beta. Namely, alpha gets replaced by alpha plus k, beta gets replaced by beta plus n minus k. So we see that if we start with a prior from the family of beta distributions, the posterior will also be in that same family. This is a beautiful property of beta distributions that can be exploited in various ways, one of which is that it actually allows for recursive ways of updating the posterior of theta as we get more and more observations. We will now continue with the problem of inferring the unknown bias of a certain coin for which we have a certain prior distribution and of which we observe the number of heads in n independent coin tosses. We have already seen that if we assume a uniform prior, the posterior takes this particular form, which comes from the family of beta distributions. What we want to do now is to actually derive point estimates. That is, instead of just providing the posterior, we would like to select a specific estimate for the unknown bias. Let us look at the maximum a posteriori probability estimate. How can we find it? By definition, the map estimate is that value of theta that maximizes the posterior, the value of theta at which the posterior is largest. Now, instead of maximizing the posterior, it is more convenient in this example to maximize the logarithm of the posterior, and the logarithm is k times log theta plus n minus k times the log of 1 minus theta. To carry out the maximization over theta, we form the derivative with respect to theta and set that derivative to 0. So the derivative of the first term is k over theta, and the derivative of the second term is n minus k over this quantity, 1 minus theta. But because of the minus here, when we apply the chain rule, actually this plus sign here is going to become a minus sign. And now we set this derivative to 0. We carry out the algebra, which is rather simple, and the end result that you will find is that the estimate is equal to k over n. Notice that this is lowercase k. We are told the specific value of heads that has been observed, so little k is a number, and our estimate accordingly is a number. This answer makes perfect sense. A very reasonable way of estimating the probability of heads of a certain coin is to look at the number of heads obtained and divide by the total number of trials. So we see that the map estimate turns out to be a quite natural one. How about the corresponding estimator? Recall the distinction that the estimator is a random variable that tells us what the estimate is going to be as a function of the random variable that is going to be observed. The estimator is uppercase k divided by little n. So it is a random variable whose value is determined by the value of the random variable capital K. If the random variable capital K happens to take on this specific value little k, then our estimator, this random variable, will be taking this specific value, which is the estimate. And let us now compare with an alternative way of estimating theta. We will consider estimating theta by forming the conditional expectation of theta given the specific number of heads that we have observed. This is what we call the LMS, or least mean squares estimate. To calculate this conditional expectation, all that we need to do is to form the integral of theta times the density of theta, but since it's a conditional expectation, we need to take the conditional density of theta. And the integral ranges from 0 to 1 because this is the range of our random variable theta. Now, what is this? We have a formula for the posterior density, so we need to just multiply this expression here by theta and then integrate. This term here is a constant, so it can be pulled outside the integral. And inside the integral, we are left with this term times theta, which changes the exponent of theta to k plus 1. Then we have 1 minus theta to the power n minus k d theta. At this point, we need to do some calculations. What is d of nk? D of nk is the normalizing constant of this PDF. For this to be a PDF and to integrate to 1, d of nk has to be equal to the integral of this expression from 0 to 1. So we need to somehow be able to evaluate this integral. Here we will be helped by the following very nice formula. This formula tells us that the integral of such a function of theta from 0 to 1 is equal to this very nice and simple expression. Of course, this formula is only valid when these factorials make sense, so we assume that alpha is non-negative and beta is non-negative. How is this formula derived? There's various algebraic or calculus-style derivations. One possibility is to use integration by parts, and there are also other tricks for deriving it. It turns out that there is also a very clever probabilistic proof of this fact, but in any case, we will not derive it. We will just take it as a fact that comes to us from calculus. And now, let us apply this formula. D of nk is equal to the integral of this expression, which is of this form, with alpha equal to k and beta equal to n minus k. So d of nk takes the form alpha is k, beta is n minus k, and then in the denominator we have the sum of the two indices plus 1, so it's going to be k plus n minus k, that gives us n, and then there's a plus 1. And how about this integral? Well, this integral is also of the form that we have up here, but now we have alpha equal to k plus 1, beta is n minus k, and in the denominator we have the sum of the indices plus 1. So when we add these indices, we get n plus 1, and then we get another factor of 1, which gives us an n plus 2. This looks formidable, but actually there's a lot of simplifications. This term here cancels with that term. K plus 1 factorial divided by k factorial, what is it? It is just a factor of k plus 1. And what do we have here? This term is in the denominator of the denominator, so it can be moved up to the numerator. We have n plus 1 factorial divided by n plus 2 factorial. This is just n plus 2. And this is the final form of the answer. This is what the conditional expectation of theta is. So now we can compare the two estimates that we have, the map estimate and the conditional expectation estimate. They're fairly similar, but not exactly the same. This means that the mean of a beta distribution is not the same as the point at which the distribution is highest. On the other hand, if n is a very large number, this expression is going to be approximately equal to k over n when n is large, and so in the limit of large n, the two estimators will not be very different from each other. In this lecture sequence, we introduced quite a few new concepts and went through a fair number of examples. So for this reason, it is useful now to just take stock and summarize the key ideas and concepts. The starting point in a Bayesian inference problem is the following. There is an unknown parameter theta, and we are given a prior distribution for that parameter. We are also given a model for the observations x in terms of a distribution that depends on the unknown parameter theta. The inference problem is as follows. We will be given the value of the random variable x, and then we want to find the posterior distribution of theta. That is, given this particular value of x, what is the conditional distribution of theta? In the case where theta is discrete, this will be in terms of a PMF. If theta is continuous, this would be a PDF. We find the posterior distribution by using an appropriate version of the Bayes rule, and here we have four different combinations or four choices depending on which variables are discrete or continuous. This is a complete solution to a Bayesian inference problem, a posterior distribution. But if we want to come up with a single guess of what theta is, then we use a so-called estimator. What an estimator does is that it calculates a certain value as a function of the observed data. So G describes the way that the data are processed. Because x is random, the estimator itself will be a random variable. But once we obtain a specific value of our random variable and we apply this particular estimator, then we get the realized value of the estimator. So we apply G now to the lowercase x, and this gives us an estimate, which is actually a number. We have seen two particular ways of constructing estimates or estimators. One of them is the maximum a posteriori probability rule, in which we choose an estimate that maximizes the posterior distribution. So in the case where theta is discrete, this finds the value of theta, which is the most likely one given our observation. And similarly, in the continuous case, it finds a value of theta at which the conditional PDF of theta would be largest. Another estimator is the one that we call the LMS or least mean squares estimator, which calculates the conditional expectation of the unknown parameter given the observations that we have obtained. Finally, we may be interested in evaluating the performance of a given estimator. For hypothesis testing problems, we're interested in the probability of error. And we have the conditional probability of error. Given the data that I have just observed, and given that I'm using a specific estimator, what is the probability that I make a mistake? And then there's the overall evaluation of the estimator. How well does it do on the average before I know what x is going to be? And this is just the probability that I will be making an incorrect decision. For estimation problems, on the other hand, we're interested in the distance between our estimates from the true value of theta. And this leads us to the following conditional mean squared error. Given that we have already obtained an observation and we come up with an estimator, in particular the value of the estimator at this time will be completely determined by the data that we obtained, but theta, the unknown parameter, remains random, and there's going to be a certain squared error. We find the conditional expectation of this squared error in this particular situation where we have obtained a specific value of the random variable capital X. On the other hand, if we're looking at the estimator more generally, how well it does on the average, then we look at the unconditional mean squared error, and this gives us an overall performance evaluation. How do we calculate these performance measures? Here we live in a conditional universe, and in a Bayesian estimation problem, at some point we do calculate the posterior distribution of theta given the measurements. So these calculations involved here consist of just an integration or summation using the conditional distribution. For example, here we would integrate this quantity using the conditional density of theta given the particular value that we have obtained. If we want to now calculate the unconditional performance, then we will have to use the total probability or expectation theorem. And in that case, we can average over all the possible values of x to find the overall error. So all of the calculations involve tools and equations that we have seen and that we have used in the past. So it is just a matter of connecting those tools with the specific new concepts that we have introduced here.